Behold, the Gyro Gunsight. Hello everyone and welcome to another video on our own devices. I'm G.G.S, and this is part 2 of my ongoing series on reflector or reflex gunsights. In part 1, we looked at the early evolution of this technology and 2 examples that were widely used by Commonwealth Air Forces during the Second World War, the Barnstard Mk.II fixed and Mk.III free gunsight. Now, as I mentioned at the end of that video, while reflector gunsights were certainly a vast improvement over traditional iron sights, they still did not solve the fundamental problem of aerial gunnery, which is calculating the correct lead or deflection needed to hit a distant moving target. And doing this requires you to know all sorts of variables, including the size, range, and relative speed of the target, which is really hard to do under combat conditions without a whole bunch of training and practice. And so, just before the start of the Second World War, engineers came up with a variety of what are known as gyroscopic or later radar gunsights to perform these calculations automatically. And that is what we will be looking at today. But first, a quick word from this video's sponsor, FlexiSpot. Now, I've never flown in a warbird before, but I would imagine spending hours in a cramped, cold cockpit or turret would be extremely uncomfortable. And for the longest time, I thought the same thing about standing desks. But when FlexiSpot approached me about a sponsorship, I got curious and decided to give it a try. And I was pleasantly surprised. This is surprisingly comfortable. In fact, I edited and researched this entire video on this very desk. So let me tell you a little more about it. Now, what sets the FlexiSpot E7 Plus apart from most standing desks on the market is its 4-leg, 3-stage design, which gives it a load capacity of up to 245 kilograms or 540 pounds static, or 200 kilograms or 440 pounds dynamic, more than double that of the closest market competitor, the Uplift V2, meaning it can hold all your office essentials: typewriter, dictation machine, check writer, adding machine, and even the office cat. This design also gives the E7 Plus greater stability and allows it to smoothly raise up to 131 centimeters or 52 inches, making it perfect for taller people like me, or even extremely tall cats. Height is easily adjusted using this keypad with built-in USB port for charging accessories. And on top of all that, it's one of the most affordable standing desks on the market, with most comparable desks exceeding $1,000 in price, and comes with a standard 15-year warranty and 30-day risk-free return service. It's also really easy to put together. In fact, Shadow did most of the work. And if you want to try one of these out for yourself, simply follow the link in the description or the pinned comment and enter the promo code YTE7P50 to get $50 off your E7 Plus or E7 Premium standing desk. Thank you so much to FlexiSpot for sponsoring this video, and back to Gyro Gunsights. Now, the principle of the Gyro Gunsight was conceived as early as 1917 by Wing Commander Lawrence Wackett and Captain Melville Jones. The basic idea is that the deflection required to hit a crossing target is equal to the rate of turn of the firing aircraft times the time of flight of its projectiles. Thus, if you know the muzzle velocity of your weapons and can measure your rate of turn using a gyroscope, you can automatically calculate proper deflection. In Wackett and Jones's concept, a regular ring and bead sight is fixed to a gyroscope such that if the attacking aircraft turns to track a crossing aircraft, gyroscopic resistance holds back the sight relative to the heading of the aircraft and its guns. So long as the pilot keeps the target in the gyro-corrected sights, the guns will automatically lead the target by the proper amount. Yet despite the theoretical elegance of the idea, in 1917 it probably would have been infeasible to practically implement, and so Wackett and Jones's concept did not gain any traction. It wouldn't be until a full 2 decades later that the Air Ministry finally began to pay attention. Now, as I mentioned in my previous video, in 1938, Europe was going through the Munich crisis, and the RAF was arming up for a potential war. As part of this effort, the Air Staff and the Committee for the Scientific Survey of Air Defense, headed by Henry Tizard, who later led the 1940 Tizard mission to share British technical developments with the United States, arranged a series of exercises at Northolt to evaluate the capabilities of RAF Fighter Command. Simulated aerial combat was undertaken using Gloucester Gladiators fitted with brand new Mk.II reflector gun sights and gun cameras to record the results. Unfortunately, these trials revealed that pilots' accuracy when making deflection shots was woefully inadequate, and that some sort of correcting or predicting gun sight would be needed if the RAF was to stand any chance against the Luftwaffe, and development of such a gun sight was given top priority by the Air Ministry. The first prototype British predicting gun sights were tested aboard Hawker Hurricane fighters and Fraser-Nash FN-25 turrets aboard Vickers Wellington bombers in October 1939. While the first production versions, manufactured by Ferranti Limited and Elliott Brothers Limited, entered service in 1941 as the Gyro Gunsight or G.G.S. Mark I. Initially fitted to Hurricanes and bolt-on-pull Defiance as well as Wellington turrets, the Mark I was found to be highly effective. Indeed, Wellington gunners reported a full 50% improvement in their marksmanship. However, the sight also suffered from a number of serious drawbacks. For one thing, it was extremely bulky, blocking much of the gunner's forward view. Also, since the Mark I was largely based on the optics of the earlier Ross G1 prismatic gun sight, it had an extremely small sighting aperture, meaning a pilot or gunner had to press their face right up to the sight to use it. This, in turn, made targets very hard to spot and track and increased the risk of head injury during violent maneuvers or hard landings. And finally, the sight was not illuminated, meaning it couldn't be used at night, and was overly sensitive, with the reticle too easily drifting out of sight and taking too long to reset. As a result, the Air Ministry was forced to halt full-scale production of the Mark I, with existing units being pressed into service for training while they developed an improved Mark II version. However, some squadrons of RAF Coastal Command continued to use the Mark I operationally, despite its disadvantages. Introduced in July 1943, the G.G.S. Mark II took the same basic mechanism as the Mark I and integrated it into an illuminated reflector gun sight like the earlier fixed Mark II and Mark III. This not only opened up the gunner's field of view, making targets easier to spot and track, but also allowed the sight to be used at night or in overcast conditions. Now, I think that's enough backstory for now. Let's have a look at some actual hardware. I have here a G.G.S. Mark IV-B, which is a direct descendant of the Mark II, first used aboard Gloucester Meteor jet fighters near the end of the Second World War. This example is a post-war Royal Canadian Air Force Mark unit and would have been fitted to the de Havilland Vampire, which was operated by Canada from 1946 to 1956 when it was replaced by the Canadair CF-86 Sabre. This is stored in a very heavy-duty metal case, which has a little window with a piece of paper impregnated with copper sulphate, which changes color from blue to pink to indicate if moisture has infiltrated the case. To open the case, we undo these 6 wing head bolts. The outer lid lifts off, and we can then pull out the inner lid, to which the sight itself is bolted upside down. And inside the case, you can see a whole lot of silica gel desiccant packets, again to keep the unit dry. On the side of the unit, we have a data plate reading G.G.S. Mark IV-B and giving the operating voltage as 24 volts DC, and this is supplied from the aircraft's main electrical system through this connector. Sadly, there appears to be some sort of fault in the wiring of this unit because no matter what I try, I simply cannot get it to fire up, so unfortunately I can't really demonstrate it to you. Thankfully, however, there are a number of wartime training films that demonstrate exactly how this is meant to operate. Anyway, at the front we have a reflector screen or beam splitter like on a regular reflector gun sight, but beneath it we find not one but 2 collimator lenses. Indeed, this sight integrates 2 separate optical systems, one fixed, one gyroscopically controlled. We also have a tinted sunscreen to reduce glare, which can be extended and retracted using this lever on the left. A big rubber pad to prevent the pilot from cracking their skull open during violent maneuvers or hard landings, and a dial for setting the wingspan of the aircraft you are shooting at. As I mentioned at the start of this series, a larger aircraft farther away might look very similar to a smaller aircraft closer up, yet require significantly different deflection in order to hit, so knowing the type of aircraft and its size is essential. On this unit, only the target wingspan is given in feet, though on the Mark II, a number of common enemy aircraft were also marked on the dial for easy reference. For example, the Focke-Wulf FW-190 and the Junkers Ju-88. Finally, this dial on the left side of the sight adjusts for the range of the target. Now, there were 2 main versions of the G.G.S. Mark II, the Mark II-D for use in fighter aircraft, and the Mark II-C for use in turrets. These work in the exact same fashion, but differed slightly in the arrangement of their peripheral controls. Right, so to use one of these sights, you first reach to one of various control boxes and flip the on-off switch. You would then see 2 reticles projected on the reflector screen. On the left, fixed crosshairs like on a regular Mark II or Mark III gun sight, which was mainly used to harmonize the guns, carry out ground attacks, or as a backup in case the gyro mechanism failed. And on the right, a gyroscope-controlled reticle comprising a central dot and a ring of 6 diamond-shaped pips. When you look straight down the middle of the sight, your brain superimposed the two reticles so they appeared concentric. The same control box holding the on-off switch also included a display selector knob with 4 positions: fixed, which displayed only the fixed reticle; fixed gyro, which displayed both reticles; gyro day, which displayed only the gyro reticle; and gyro night, which disabled the sight's normal ranging functions and fixed its range at 200 yards. This is because judging an attacking aircraft's range at night is extremely difficult. Typically, you would only be shooting at the flame coming out of the aircraft's exhaust stacks. You could also adjust the reticle brightness using a dimmer ring on the control box and mask off the fixed reticle ring, leaving only the central cross, by pulling this lever on the left of the sight. And this is derived from the Beaumont modification mentioned in Part 1. And yes, it is Beaumont, not Beaumont. You can blame my French-Canadian ass for that one, eh? Anyway, the next step in setting up the sight was to use another pair of selectors on a separate control box to set the aircraft's altitude and speed. This was to compensate for windage, that is, the effect of crosswind on bullet trajectory. For example, the higher the airspeed, the greater the windage effect, whereas the higher the altitude, the lower the windage and the time of flight, since the atmosphere is thinner and has less effect on the trajectory of the projectiles. In turret installations, the sight also compensated for the horizontal angle or azimuth of the turret, since the greater the azimuth relative to the line of flight of the aircraft, the greater the windage effect, since you're shooting across from the wind. And finally, in some installations, there was also a ballistics controller box that compensated for the ballistic drop of different types of ammunition, such as high-velocity machine gun bullets, cannon shells, and air-to-ground rockets. Next, you identified the target aircraft you were attacking or defending against and entered its wingspan using the dial on the front, which expanded or contracted the gyro reticle. Aircraft identification was a fundamental part of air gunnery training, with fighter pilots and defensive gunners being extensively drilled on how to identify every type of enemy aircraft at a glance. And to learn more about these training methods, please check out my previous video on the subject, link in the description. Finally, you set the target range. Now, this could technically be done by simply turning this range dial on the left side of the sight, but in practice, this mechanism was designed to be operated remotely via a Bowden cable system connected to this pulley on the dial. On the Mk.IV or the Mk.II, the system was operated by a twist handle on the fighter aircraft's throttle, while on the Mk.II turret variant, it was operated using a set of foot pedals. In either case, you use these controls to dilate or contract the gyro reticles so that the target aircraft's wingspan just fit inside the circle of diamond-shaped pips. The minimum range of the sight, at which point the reticle would expand no further, was set at 200 yards. And at this range, you could aim at the center of the target and be fairly certain to hit something. Anyway, when you banked your fighter aircraft or traversed your turret to follow a crossing aircraft, the gyro reticle would deflect relative to the fixed crosshairs, the degree of deflection being directly proportional to your rate of turn, and thus the relative speed of the target. Thus, so long as you set the appropriate wingspan and kept the aircraft centered in the gyro reticle with the wingtips just touching the inside of the pips, your shots would land on target every time. So all of that is really, really cool, but how does it actually work? Well, the internal mechanism of this sight is actually a lot simpler than you might think. So let's take it apart and let me show you exactly what I mean. Right, so the first step in disassembling this sight is to undo these 3 top screws on the rear of the casing and this small screw on the side, which allows us to remove the sunshade. We then remove the rest of these screws, and the whole rear panel slides right out. On the left-hand side, we have a fixed circular mirror, which is part of the regular fixed reflector gun sight system. At the rear, you can see a little glass window with an etched crosshair reticle. If we go to the front and remove this panel, we can see 2 incandescent light bulbs that illuminate the sight. Light from the right-hand bulb shines through the etched window, and the resulting reticle image is reflected rearward by the fixed circular mirror, up by this 45-degree mirror through a collimator lens, and finally back by the reflector screen into the gunner's eye. This produces a fixed illuminated reticle focused at infinity, just like in a regular reflector gun sight. But it's on the right side of this housing that things really get interesting. This mirror is connected via a universal or hooks joint to a gyroscope contained in this cylindrical housing, which is driven at 4,000 RPM by an electric motor in this other housing via a built-in pulley system. When you are flying straight and level, the mirror remains perpendicular to the axis of the gyroscope and reflects the reticle image from the second projector system directly back onto the 45-degree mirror, causing both reticles to exactly coincide. However, as you begin to bank, gyroscopic resistance causes the angle of the mirror to lag behind that of the sight and the aircraft it is mounted to, in turn causing the gyro-controlled reticle to deflect relative to the fixed reticle. Now, another key feature of this system is this aluminum dome or rotor on the mirror shaft, which is magnetically suspended by these two pairs of electromagnets. The vertical pair are known as gravity coils and the horizontal pair as azimuth coils, and they serve a number of purposes. Firstly, they provide a damping effect which prevents the gyroscope and the mirror from precessing too wildly during violent maneuvers, but more importantly, they are a key component of the ranging system. So, as I mentioned, an aircraft farther away will require greater deflection than an aircraft closer up, and so when you twist the throttle handle or apply the pedals to change the range of the reticle, you're also operating a rheostat that varies the amount of current being fed to the coils and thus the strength of the suspending magnetic field. And so, for example, for an aircraft farther away, you're going to be applying less current and thus a weaker magnetic field, allowing the gyroscope and the mirror and thus the reticle to deflect farther, and vice versa. Finally, the coils allow the sight readout to be calibrated for altitude, airspeed, ballistic drop, and other variables via the aforementioned control boxes. Now, being based on the Ross G1 prismatic gun sight, the G.G.S Mk.I used a slightly different mechanism, though the basic operating principle was identical. Instead of a mirror, the gyroscope spindle assembly was connected to a sliding linkage and a piece of clear celluloid with a black reticle printed on it. A second fixed reticle was also integrated into the sight's optics. When the pilot or gunner tracked a crossing target, deflection of the gyroscope relative to the sight and the aircraft moved the second reticle relative to the fixed reticle, automatically calculating and displaying the proper deflection. Now, the last key feature of this sight is the ranging mechanism. If we look inside the right-hand side of the gun sight housing, we can see this strange aperture assembly between the second projector lamp and the gyro mirror. This comprises two masking plates or graticules, a span graticule with 6 straight radial lines rotated by the target wingspan knob, and the range graticule with 6 curved radial lines rotated by the ranging mechanism. As you can see, as these graticules rotate past each other, it causes the ring of diamond-shaped pips making up the gyro reticle to expand and contract in a manner corresponding to the apparent size of the given aircraft at different ranges. Now, a few last features worth pointing out include the desiccant and breather tube system. This compartment holds a cartridge of silica gel desiccant, while all air entering or exiting the sight due to changes in air pressure has to pass through a very long labyrinthine breather tube connected to the cartridge. All this prevents moisture from entering the sight and fogging up the optics. Also, a special sight recording camera was developed which fit to the top of the sight and allowed combat footage to be captured directly through the reflector screen every time the aircraft's weapons were fired. This footage could later be reviewed for training or combat effectiveness evaluation. And to learn more about these very cool devices, please check out my previous videos on the GSAP and GC16 gun cameras. Links in the description. Finally, with the advent of ejection seats, sights like these became a potentially serious hazard to the pilot. So the Mk.IV and later Mk.V G.G.S were typically fitted to a retractable mounting Type 7 that the pilot could quickly fold out of the way by pulling a handle just prior to ejection. And that, dear viewers, is how a gyro gun sight works, and while incredibly precise engineering, especially for the time period, was required to get these working properly, the basic principle that makes these work is remarkably simple, and this is the sort of ingenious analog problem solving that I love to cover on this channel. Anyway, getting back to the history of gyro gun sights, Ferranti established a purpose-built factory near Edinburgh to produce G.G.S Mk.IIs, which began rolling off the production line in November 1943. By October 1944, the factory employed 950 employees and was turning out 1,000 gyro gun sights every month. Barr and Stroud, which manufactured the Mk.II and Mk.III fixed reflector gun sights, also manufactured optical components for the G.G.S, while some G.G.S manufacture was also subcontracted to the Salford Electrical Company. Initially, fears that this sophisticated secret weapon might fall into enemy hands restricted its use to units flying over the UK, but eventually, as the advantages of this system became impossible to ignore, this rule was steadily relaxed. And initially, a lot of pilots were skeptical about this technology, but a lot of these doubts were driven by the extensive setup and unintuitive operating procedure of the Mk.I gun sight. Once they were shown the Mk.II, which eliminated most of these issues, it won over most of the remaining holdouts. By the end of the war, the G.G.S Mk.II had become the standard gun sight on nearly all British and Commonwealth fighters and bomber turrets. Versions were also licensed built by Sperry in the United States and adopted by the US Navy as the Mk.XVIII for turrets, the Mk.XXI for fighters, and the Mk.XIV for shipborne guns, and by the US Army Air Forces as the K.14. Meanwhile, the Germans had independently hit upon many of the same principles. And starting in 1935, various firms, including Carl Zeiss and Askania, developed a variety of gyroscopic gun sights under the designation EZ, short for Eigen- und Seilgeschwindigkeitsgestelltes Visier, or Self- and Indicated Airspeed Controlled Sight. German, why are you like this? Anyway, initially there was very little interest from the Reich Air Ministry, and in testing, the German gyro gun sights proved very bulky, heavy, unstable, inaccurate, and labor-intensive to produce. It wasn't until July 1944 when Allied aircraft equipped with gyro gun sights began operating en masse over the European continent that the Luftwaffe installed some 200 early production EZ-42 sights on Focke-Wulf FW-190 and Messerschmitt Me-262 fighters for field trials. However, faulty installation rendered these sights all but useless, with most pilots locking theirs down for use as regular fixed reflector sights. Furthermore, Me-262 pilots found it very difficult to continuously adjust the sight's range while closing on targets at the high speeds made possible by jet propulsion. Which leads me perfectly into the last topic I want to briefly cover in this video. For while gyro gun sights were state-of-the-art and increased gunners' accuracy by between 50 and 100%, they became even more effective when combined with the other great technological breakthrough of the war, radar. Now, radar had been developed in both Britain and Germany before the war, famously playing a key role in the 1940 Battle of Britain. However, it wasn't until the development of the cavity magnetron by John Randall and Harry Boot at the University of Birmingham in 1940 that truly efficient centimetric radar, light and compact enough to be carried aboard aircraft, became possible. And if you want to learn more about the fascinating development of radar, I've written a number of videos on the topic over on Today I Found Out. You can also check out my previous video on radar chaff and other countermeasures. Links, as always, in the description. Anyway, the first magnetron-based aircraft interception, or AI radar set, the Mk.VII, entered service aboard Bristol Beaufighter and de Havilland Mosquito night fighters in late 1941, and was supplanted by the even more sophisticated Mk.VIII in early 1942. Originally, radar intercepts were a two-person affair, with the radar operator reading the radar scope and guiding the pilot towards the target. But late in the war, a number of Mosquitoes were fitted with a system that projected the image from the tube onto the pilot's windscreen, allowing him to see and intercept targets directly. And in a sense, this was one of the earliest versions of what we would now recognize as a heads-up display, or HUD. A similar system, formerly known as the Automatic Gun Laying Turret, or Fraser-Nash FN-121, and codenamed Village Inn, or Z equipment, was also developed, which fed target position and range data from a small scanning radar set into a modified G.G.S. Mk.II gyro gun sight. Small numbers of these units were fitted to Avro Lancaster and Avro Lincoln rear turrets in the final months of the war. An even more straightforward application of radar to gyro gun sights was in automating range measurement, freeing the pilot from having to continuously and manually adjust the reticle in order to keep the target boxed in. Now, I was originally going to wait until I got my hands on some actual hardware to make a separate video on radar gun sights, but as luck would have it, late in the production of this video I stumbled upon this Ferranti G.G.S. Mk.VIII, which was fitted to a number of post-war British jets like the Hawker Hunter and Supermarine Scimitar. Overall, this is nearly identical to the Mk.IV, but as you can see on the left-hand side here, the range control is driven not by a pulley connected to the throttle, but rather a servo motor connected via this large cable to the aircraft's radar. And just above the range drive are these green and red lights, which indicate whether the radar is getting a return from the target, and are powered by this smaller cable here. And finally, at the back of the sight are two rotating shafts with adjustment knobs, and these allow you to tilt the fixed mirror up and down or side to side in order to harmonize the aircraft's weapons. Unfortunately, this sight has proven very difficult to disassemble without damaging it, so in the interest of preservation I won't force it. Instead, I can show you these images from a manual on the very similar G.G.S. Mk.V. A more well-known version of this system was the APG-30 used on the North American F-86 Sabre, which used range data from a small X-band radar mounted in the upper lip of the aircraft's nose intake. This sight allowed accurate deflection shots to be made out to ranges of 1.8 kilometers or 1.1 miles, and is credited with giving the Sabre an edge over the Soviet Mk.XV during the Korean War, despite the two aircraft being otherwise evenly matched. I also eventually want to do a video on reflector sights for small arms, but again, I am still accumulating the artifacts I need to make that video, so for now this will only be a two-part series. Anyway, I hope you enjoyed that. Thank you so much for watching, and I'll see you next time in another episode where we'll look at yet more fascinating gun sights and other devices just like this. Until then, I'm G.G.S from Our Own Devices. Have a great day.